Okay, so here we are talking about the solution for quiz 4, just the part about computing the equivalence classes. So we have two sets, 2 bar, which consists of 2 elements, and 5 bar, which consists of 5 elements. Now in the quiz, I give some examples of elements in this set, which is the set that our equivalence relation is going to be on. So all of these examples are just on finite sets. So it's maybe a bit tedious, but it is possible to list out all of the elements of the set. So if you don't know where to start, I would suggest doing this. It's not strictly necessary, but it's a good place to start. So I'm going to do that now. Okay, so now I've written out all of the elements of this set. There are 32 of them because 2 to the 5 is 32. And you can see, as I hinted at in the written up problem in the quiz, that these elements are all the 5 tuples. Like they're like ordered pairs, but there are 5 guys in each one now. So we can call them 5 tuples or quintuples. They're all the 5 tuples that have 0 or 1 in each spot. Okay, so this is the whole set. And now this is the relation that we were considering. So we say that 2 guys in this set are equivalent if when we sum up all of the entries, we get the same thing. So let's see which guys in our set are equivalent to each other. So this first guy, if we look at our first element here, and we sum up all of its elements, it's 0, so I'll just write that as a little 0 up there. And if we sum up, if we look at this row, I've kind of written them in a clever way, because everyone in this row, if we sum up each of the components of this first guy, we get 1, and then for the second guy, 0 plus 1 plus 0 plus 0 plus 0 is 1. So the sum of all of these guys is each 1. So these guys are all related to each other. Maybe I can just draw that by drawing little lines between them. Now in this second row, if we sum up this guy, 1 plus 1 plus 0 plus 0 plus 0, we get 2. Similarly, all of these guys in this row and the next row sum up to 2. So these guys themselves are all related. So we can draw lots of lines between all of them. If we look at this row, all of these guys, for each of these guys, if we sum up the components, we're going to get 3. So these guys themselves are all related. And in this row, they all sum up to 4. We can write a little 3 here and a little 4 here, just to remind ourselves. And in this row, we've just got 1 guy, and if we sum up this guy, it sums up to 5. Okay, so if we wanted to find out what the equivalence classes are, those are the sets that consist of all the guys that are related to each other. So here we have one equivalence class of all the guys that are related to this particular 5 tuple 0, 0, 0, 0, 0. There's only one guy in this equivalence class because, well, this guy is certainly related to himself because we have an equivalence relation, but he's not related to anybody else. And then if we look at this row, the second row here, these guys all make up their own equivalence class because they're all related to each other because they all have the same sum when we sum them up. And if we look at the third row, these guys are all related to each other because they all give the sum of 2. And everyone here is related to each other because they all give the sum of 3. These guys are all related to each other because they all give 4. And this guy is a little bit lonely in its own equivalence class because it's the only guy who gives a sum of 5. So we have here 6 equivalence classes. So if we were to write this out, maybe I won't do that because it would be a bit tedious, but we have one equivalence class that consists of this guy, oops, and we can notate that like this. So whenever we draw brackets around one element of an equivalence class. We're saying this is the set of all guys that are related to this one guy that we've just written down. So here, for this equivalence class, I guess I can write this one out, won't be too bad. So this equivalence class consists of these 5 guys. Okay, so we have the set of these 5 guys, and we can write this more quickly by just writing square brackets around one of the guys in this equivalence class. So we could pick any guy that we want to write here, but let me just write the first one. Okay, and this thing here, this notation here that I've written, means the set of all guys who are related to this 5-tuple 1, 0, 0, 0, 0. So that's this set here that we've just described of these 5 elements. Okay, so what's the quotient then of this set? The quotient is the set of all equivalence classes. So it's a set of sets because every equivalence class is itself a set, right? So it's a set of sets, and we can easily describe this by writing it in this, why can't I change the color here? We can write it using this notation. So our set of equivalence classes, the quotient, which is a set of equivalence classes, will have 6 elements. So let's write it over here, oops, on the side. Like this. So this set is going to have 6 elements. So the first one is going to give us the first equivalence class, so that's this guy here. Then the second one will give us this equivalence class here. And the third one is going to give us this equivalence class, so I can pick any guy in this equivalence class to put in brackets here, but I'm just going to pick the first one. And now for this one, I can write 1, 1, 1, 0, 0. And then for this one, I can write 1, 1, 1, 1, 0. And then for this one, there's only one choice, which is 1, 1, 1, 1, 1. Okay, so this is the set now of equivalence classes, the quotient. Oops, the quotient of our set. I have a typo here, so we're trying to quotient this set. So the quotient of our set just consists of 6 elements. It's these guys, which can be written in different ways in the sense that you could have a different choice here of an element. You can choose any one in the equivalence class, but it should have 6 elements that represent each of the 6 equivalence classes. Okay, so now we're looking at the problem from midterm 2 that pertains to LO6. So again, we have this 3 over bar, similar to the 2 over bar and the 5 over bar. So this is the set that consists of just 3 elements. And we're going to let f denote the set of all functions from 3 to 3. So for example, the function f from 3 to 3 defined by, say, f of 0 equals 1, f of 1 equals 1, and f of 2 equals 2 is an f. And also the function g from 3 to 3 defined by f of 0 equals, let's say, 0, f of 1 equals 2, and f of 2 equals 1, say. This is also an f. So these are some of the functions that can be an f, and hopefully it should be clear that to define or to specify any function in f, any function from 3 to 3, we just have to say where each of the elements goes, as usual, right? So we just have to say where 0 goes, where 1 goes, and where 2 goes. So there's no standard way, I would say, to notate such a function from a finite set like this to a finite set. But I think it will be pretty clear, at least for our purposes, just for this explanation, to notate a function like this by just saying first where 0 goes. So in this first example, 0 goes to 1, 1 goes to 1, and 2 goes to 2. So we can say that this notation I've just made up, 1, 1, 2, is the description or the definition of f. And sorry, this is a typo. I guess these should all be g's, since I wanted to call this function g, sorry. So g now with our new notation could be described by this symbol 0 to 1, right? Because we want to send 0 to 0, 1 to 2, and 2 to 1. Okay, so any function from 3 to 3 we can describe in this way, we can notate in this way, which is not totally standard, but I think pretty reasonable. So now we can go ahead and write down all of the elements of f. Okay, so now we have written down here all of the possible functions from 3 to 3 in our new notation. Now we just have to understand what the equivalence classes are. So the equivalence relation says that f is equivalent to g if f of 0 equals g of 0, and in our notation, this corresponds to the first component, that first number being the same, right? Because that first number in the list of 3 numbers tells us where 0 goes. So we see that, for example, these two guys are related because they both send 0 to 0, they both send 1 to 0, which is irrelevant, and this guy sends 2 to 0, this guy sends 1 to 0, which is irrelevant. We just care that they both send 0 to 0. So the first component is the same. So these two guys are related. So similarly, these two guys are related because they both send 0 to 0. These two guys are related because the first number there is the same. So these are all related. This guy is also related to all of the guys in the first row. These two are related. Okay, but this guy is not related to this guy because the 0 to 2 sends 0 to 0, and 1, 0, 0 sends 0 to 1, right? Because the first number there is different. So let me erase that just to not cause any confusion. But these two guys are related. These two guys are related. These are all related because their first number is the same. They all send 0 to 1, and then similarly all of these guys are related to each other. So we have 3 equivalence classes. So we have this guy, we have this equivalence class, and we have this equivalence class. Right, so we have 3 equivalence classes just defined by where these functions send 0. So this guy is all the functions that send 0 to 0. This guy is all the functions that send 1 to 0. And this guy is all the functions that send 2 to 0. All right, so now we have to write down the quotient. So f mod this equivalence relation is a set that has 3 elements. So it's not so hard to write down, but we have to decide how to write down the elements. So we shouldn't probably write down these elements using the notation that we've devised, although it's totally fine. You would just have to accompany that with an explanation to the reader, say me, who's looking at your answers, about what this notation means, because this is not standard notation. We just made it up as a way to easily write down elements of the set. So you could certainly write the quotient using this notation. You would just have to explain to the reader what it is. But note that with the notation that we've been using in class, lambda notation, we can kind of easily write down at least some of these functions, and we only need to write down one of them in each equivalence class. So there's some clever thinking we can do, which is that this guy here, 0, 0, 0, is the function defined by lambda x 0, right? It takes in any x, takes in 0, 1, or 2, no matter what you give it, it will spit out 0. So for our first equivalence class, we can write down lambda x 0 as the lambda x 0 with brackets around it as the equivalence class. Okay, and this one, for this one, we also have one special element, which is this guy here. This guy here, 1, 1, 1. That's defined, it could be defined by writing lambda x 1. So we can give that here as our representative. And here we can give this special element lambda x 2. Lambda x 2. Okay, so that's one choice that just uses notation that we've already used in the class and is relatively standard. You don't have to be that clever. You could just pick 3 random elements from each equivalence class, use whatever notation you've devised yourself to write these things down, but then you would have to explain to the reader or the grader what exactly your notation means. Okay, but this is one good answer. Okay, so now we're looking at the question from quiz 9, and we have a similar thing. So 3 bar, as before, is just the set 0, 1, 2. I've written out 3 bar times 3 bar, which is the set that we're taking the quotient of. So it consists of these 9 elements, all possible ordered pairs, where each component comes from the set 3 bar. And our equivalence relation is given by saying that 2 ordered pairs are the same if both of their sums are the same. So it's quite similar to, I think, the first question that we saw. So let's ask ourselves which of these guys are similar, or sorry, are equivalent to each other. So the first guy, the sum of its 2 components is 0. So I don't think it's going to be equivalent to anyone else. But the second guy, its sum of its 2 components is 1. And similarly, this guy, the sum of its 2 components is 1. So these 2 guys are related. Okay, and this guy, this 0, 2 here, if we add up its components, we of course get 2, which is the same as this guy here and the same as this guy here. Right, they all add up to 2. This guy here adds up to 3, which is the same as this guy, and this guy at the end here adds up to 4, so it isn't equivalent to anything itself. So there are these, how many are there? 1, 2, 3, 4, 5 equivalence classes. So we have this guy, we have this equivalence class. This is maybe not the most useful thing I'm doing here, circling all these guys. So we have this one here, and we have this one. So we have these 5 equivalence classes. Okay, now let's write them out. So if we take our set, we mod out by our relation. We want to know what this is, so we have to list the 5 equivalence classes. Okay, so the first one, this one here, we can write like this. Okay, but of course there's only in this equivalence class that we're writing down here, there's only just this guy 0, 0 in that equivalence class. For the second one, the equivalence class of all guys who sum up to 1, we can pick any element we want there. Let's just pick 0, 1. We could have written down 1, 0, of course. Now for the third one, we're talking about the equivalence class of all guys that sum up to 2. So we could write down any guy we want in that equivalence class, but I'm going to write here 0, 2. And I think if you look at my answer that I've given on Carmen, is probably slightly different. I probably picked different representatives. Now we're looking at the equivalence class whose guys all sum up to 3. So we can pick 1, 2. And lastly, we're looking at the equivalence class of guys that all sum up to 4. And there's only 1 in there, that's 2, 2. Okay, so we've gotten these 4 equivalence classes. So we've written down this one. Good. We've written down this one. We've written down this one. We've written down this one and this one. So we've got them all. There are 5. And so that would be a good answer to this question. Okay, so here we are looking at quiz 12. So our set that we're going to take a quotient of is p sub 2 of 2 bar, which is all of the degree 2 polynomials whose coefficients can come from the set 2 bar, or the set of 0 and 1. And so I've written out here all of the elements like I have before, and maybe it's slightly more correct for each of these guys to write like lambda x comma x squared plus x plus 1, because the function that sends x to x squared plus x plus 1, but I've just left that out to make it a bit easier to read. So we've got these 8 polynomials. Don't forget about these 2 simple guys at the end. They're still there. Okay, so our equivalence relation says that f is equivalent to g if, when we take the this indefinite integral, fx minus gx, that's a constant. And with just a little bit of calculus, we know that this, of course, means that f of x equals g of x, because actually f of x minus g of x will, or the integral of f of x minus g of x will be 0 if it's a constant, and so we can differentiate and find that f of x equals g of x. Okay, so because this equivalence relation is just equality, none of these guys here in this set are equivalent to any other guys except for, of course, themselves. So they're all in their own equivalence class, right? None of them is equivalent to any others, because none of them is actually equal to any others except for themselves. So we can easily write down the equivalence class, or the quotient of this guy, the set of all equivalence classes, which can be written like this. Okay, so keep in mind that it's not exactly the same as P2 of 2 itself, because this guy, so for example, this guy is just a different way to write the set that consists of this one element, which is this function here. Okay, so it's very similar to the set P2 of 2, except that we've got not a set of a bunch of functions, but a set of a bunch of sets, which each themselves just consist of one function. So it's kind of just like there's some extra packaging in this set that's maybe a bit annoying. Maybe we don't really need it, but it is there. It is part of this quotient. Okay, so it looks very similar to original set because each function constitutes its own equivalence class, but don't forget that there's this extra stuff going on, this extra packaging, which is that each one of these elements is not a function itself. So this guy here, this element, this first element here, is not a function itself. It's a set that consists of exactly one function, and it's exactly the same with the rest of the elements. Okay, so that's it. We've gone through all of the solutions now to all of the LO6 questions on quizzes and midterms. If you have any more questions, please put them in the discussion for LO6.